What specific problem does the new method or algorithm aim to solve?
The new method or algorithm aims to solve the problem of training data memorization in reinforcement learning from human feedback, RLHF, for code completion models. Specifically, it focuses on analyzing the risks of memorization in different stages of RLHF, such as fine-tuning, reward model training, and RL fine-tuning. The goal is to understand if and when training data can be memorized by the model, especially in sensitive areas like code completion, where leakage of user data can raise legal, commercial, and privacy concerns. The method aims to measure and mitigate the potential memorization of sensitive or proprietary information during the training of code completion models using RLHF. It also investigates how different hyperparameters, such as the KL regularization coefficient, can impact the persistence of memorization in the model. Ultimately, the new method aims to provide insights into how to prevent or reduce the risk of training data memorization in code completion models trained using RLHF, especially in scenarios where sensitive data is involved.
How does the proposed method or algorithm work, and illustrate it step by step?
The proposed method, reinforcement learning from human feedback, RLHF, works by aligning large language models with user preferences through three main phases. First, the model is fine-tuned on a specific dataset for the task of code completion. Second, a reward model is created to evaluate the quality of the model's output based on human feedback. The reward model assigns scores to code completions, with positive scores for good completions and negative scores for bad ones. Finally, the fine-tuned model is optimized to generate completions that maximize the scores assigned by the reward model through reinforcement learning. To illustrate this process step by step, 1. The model is fine-tuned on a dataset specific to code completion, enabling it to understand basic syntax and style of coding languages. 2. A reward model is trained to evaluate the quality of code completions based on human preferences, assigning positive scores to good completions and negative scores to bad ones. 3. The fine-tuned model is then further optimized through reinforcement learning to generate completions that maximize the scores given by the reward model. 4. During reinforcement learning fine-tuning, the model is penalized for deviating too much from its initial fine-tuned state to prevent overfitting to the reward model scores. 5. The process ensures that the model learns to generate code completions that align with user preferences, balancing between memorization of training data and generating diverse and contextually appropriate completions. 6. By carefully adjusting hyperparameters, such as the KL regularization coefficient, the model can be guided to avoid over-optimizing on specific examples and reduce the risk of memorization of sensitive data. 7. The method allows for the incorporation of human feedback into the training process, improving the quality of code completions while minimizing the risk of memorization of sensitive or proprietary information. 8. The analysis of memorization at each stage of RLHF provides insights into how training data can be memorized and how the risk of memorization can be mitigated through appropriate training strategies and hyperparameter selection.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using reinforcement learning from human feedback, RLHF, for aligning large language models with user preferences in code completion tasks are significant. The method of RLHF allows for the optimization of code completion models to generate suggestions that align with user preferences, which can lead to improved user satisfaction and productivity. The use of RLHF enables the model to learn human preferences, both desired and undesired, through reward modeling, and distills this knowledge into the model via reinforcement learning. This approach helps in creating code completions that are more tailored to individual developer preferences, such as favoring shorter and more efficient code or prioritizing readability and comments. Additionally, RLHF helps in mitigating the risks of memorization of sensitive data, as shown in the analysis conducted in the paper. By carefully controlling the KL regularization coefficient during RL fine-tuning, the risk of memorization of training data is minimized, allowing organizations to leverage valuable data in reward model training without significant risks of data leakage. Furthermore, the method provides insights into how memorization can occur in different stages of the RLHF process, aiding in understanding and addressing potential privacy and security concerns. Overall, the use of RLHF in code completion tasks offers a systematic and effective way to align large language models with user preferences while managing the risks associated with data memorization, ultimately enhancing the quality and usability of code completion assistance.
How is the method validated or tested?
The method is validated or tested by measuring the memorization of training data in 3 phases of reinforcement learning from human feedback, RLHF, fine-tuning, reward model training, and RL fine-tuning. The validation process involves analyzing the persistence of memorization from fine-tuning through RL fine-tuning, assessing the memorization of reward model training data through RL fine-tuning, and measuring the rate of prompt memorization in RL fine-tuning. The study carefully examines the impact of each phase on data memorization, using specific criteria such as normalized edit distance and counterfactual memorization to determine if examples are memorized. The experiments involve training models on synthetic Python datasets, splitting the data into subsets to measure different types of memorization, and varying hyperparameters like the KL regularization coefficient to observe its effect on memorization rates. The results show the percentage of examples that are memorized in each phase, with detailed analysis provided for each stage of the RLHF process. The study also discusses the implications of the findings, such as the low risk of memorization of sensitive data during reward model training and the importance of considering confounders in the memorization analysis.
What results were achieved with this new method?
The results achieved with the new method showed that training examples that were memorized during the fine-tuning stage remained memorized after RL fine-tuning, with approximately 43 to 47% of examples persisting. The memorization of sensitive data in the reward model training data was very low, with only 0.9% of examples being memorized. The study also found that the memorization of prompts used during RL fine-tuning was possible, but the risk was low, with fewer than 0.5% of prompts being memorized after 70 epochs of RL fine-tuning. The impact of KL regularization on memorization was also analyzed, showing that a smaller alpha coefficient allowed for increased memorization. Additionally, the study highlighted the potential for organizations to use valuable data in reward model training without significant risks of sensitive information leakage. The results demonstrated the complexity of analyzing where memorization can arise in the RLHF process and how it can persist through different stages, with the risks being modulated by hyperparameters used during RL fine-tuning.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the potential for memorization of training data at various stages of the reinforcement learning from human feedback (RLHF) process. Specifically, the paper highlights that training examples memorized during the fine-tuning stage may persist after RL fine-tuning, indicating a risk of data memorization throughout the process. Additionally, there is a concern regarding the memorization of sensitive information, such as P-like data, which could lead to privacy and security issues if leaked through model interactions. Another limitation is the reliance on the reward model signal during RL fine-tuning, which may not always prevent memorization of reward model training data by the RL fine-tuned model. The paper also mentions the challenge of defining and measuring memorization accurately, especially in the context of code completion, where confounding factors like repeated code structures can impact the analysis. Furthermore, the study acknowledges the difficulty in assessing the risk of sensitive data leakage, particularly in larger, real-world datasets with unknown sensitive information. Lastly, The method's dependence on hyperparameters, such as the strength of the KL divergence penalty during RL fine-tuning, introduces variability in the risk of memorization, which could be a limitation in ensuring consistent results across different experiments.